Hi everyone. So today in our free response series, we are going to do a pendulum problem. But because we are still in the unit for kinematics, this is actually a pendulum situation that we are going to use to calculate an experimental value for the gravitational acceleration or free fall acceleration at some location. So let's go look at what the problem is giving you. They tell you that you are conducting an experiment, and again, the purpose is to calculate GU at some unknown location. Okay, that's what the U stands for. And then for that, they use a measurement apparatus that consists of a simple pendulum that is swinging past a photogate located at the pendulum's lowest point. So basically what they're telling you is something like this. You have the pendulum hanging somehow, and then they pull the pendulum to the side, they release it, and of course the pendulum is going to swing back and forth like this, back and forth, and then at the lowest point, which is basically the middle of the trajectory, they locate a photogate, and that photogate is going to be able to measure the time t10 for the pendulum to undergo 10 full oscillations. Okay, so those 10 full oscillations are the time that is recorded over here on the second column of the table. Now they tell you that there are 4 versions of this apparatus, each with different length. Now what's the point here? If you remember from your basic physics, the period of a pendulum depends directly on the length of the string. Basically, by the relationship, period is equal to 2 pi times the square root of the length divided by the gravitational acceleration. So this formula is going to be very important later. But right now, the important part is that you are getting different values for the time because you have different lengths. 12 centimeters, 18 centimeters, 21, 32 centimeters, etc. And so you get different values for the time, and therefore you're going to get different periods. Now they want you to give the value for those periods. Look at what they are requesting here. For each pendulum, calculate the period t and the square of the period. Use a reasonable number of significant figures. What does that mean? In general, you want to try and conserve all the values that you have here with 3 or 4 significant figures as they are given. Now for the period, because this is the time for 10 oscillations, you don't really need a calculator. You just need to move the decimal point one space to the left. And so the period here is 0.762, 0.889. Now, if you want to conserve the significant figures, this is 1.009. The other one is 1.208. Now, you do need a calculator to get the square of the period. You're going to get more decimals than these, but if you conserve the amount of significant figures, you want 3 significant figures for this, 0.581, then 0.790, then 1.018, and finally 1.459 squared seconds. So that was what they requested in part A. Next, they want you to do something about those values. They want you to make a best fit line. Let's look at the instructions for part B. On the axis below, plot the square of the period versus the length of the pendulum. Draw a best fit straight line for this data. Now, we have to once again consider carefully what is it that they are giving you. On the horizontal axis, what you have is the length of the pendulum given in centimeters. On the vertical axis is the square of the period. So they are asking you to use the first and fourth columns of the table, of which we have a copy here. Now, the assumption here is that you are going to get a straight line. We should be able to corroborate that by placing the dots and actually just looking at it. So because the length is in centimeters, you are here at 12 centimeters and 0.581. That's approximately here. Then you have 18 centimeters and 0.790, which is a little below 0.8. Next, 21 centimeters, 1.018, almost exactly 1. And finally, 32 centimeters and 1.459, which is somewhere around that. So it does look approximately like there is a straight line there. Now, of course, you're going to do it with a ruler. Here, I'm going to do it with a line like this. And then remember that when you make a best fit, you try to get as close as possible to all of the points. Try to minimize the distance from the line to each point. And you also um, try to leave a few points a little above and a little below the line so that this is sort of the average. And so that is your best fit straight line for this data. But of course, um, it is irrelevant to have a line just by itself. The whole point of a straight line from a best fit model is to get the meaning of either the y-intercept or the slope. Let's look at what they're asking for part C. What they are telling you now is, assuming that each pendulum undergoes small amplitude oscillations from your fit, determine the experimental value gx of the acceleration due to gravity at this unknown location. What do they mean by this? First of all, what is meant by this idea of small amplitude? Remember the formula that we discussed before. The period of a pendulum is equal to 2 times pi times the square root of the length of the string divided by g. Now, if you remember, the whole idea was that the motion of the pendulum is described by a differential equation. And that differential equation worked under a very clear assumption, which was that the angle theta that represents the amplitude of oscillation has to be small. Basically, what we are saying is this formula is only true for small angles. That's what is meant by small amplitude oscillation. It doesn't work if the angle is too large. So what do we mean by too large? Basically, your angle in radians has to be approximately less than pi over 12 or 15 degrees to either side of the vertical. So if your angle is like that, which is what they tell you to assume, you can use this formula. Now, why do we have to use this formula? The whole idea is, remember, you have in this graph the square of the period versus the length of the pendulum. So if you look at the equation, you can make it look like this. Square of the period is equal to 4 pi squared times the length divided by g. The square root cancels with a square. And if you get the constants together, then the square of the period is equal to 4 pi squared divided by g times L. Now remember that the vertical axis was given by this t squared, and the horizontal axis was given by the length of the pendulum. So this means that this equation looks very much like the classical straight line y equals mx, which means that our interpretation of the slope of this line is that the slope is the expression for pi squared divided by g. In this case, we're going to call it gx, which is the experimental value of g that we are trying to find. So if we get the slope of that line, there is a chance that we can get a value for the experimental acceleration due to gravity. Let's look back at the line and see if we can determine its slope with some degree of accuracy. First, you need 2 points, and those 2 points need to be directly on the line. One good point to do that will be this. The coordinates of that point are 2 centimeters on the horizontal axis, 0.1 square seconds on the vertical axis. Another good point will be something, for example, like this, which is, I believe, 28 centimeters on the horizontal axis, 1.3 square seconds on the vertical axis. And so if we use these 2 coordinates to get the slope, what you have on the left-hand side of this equation is, 1.3 squared seconds minus 0.1 square seconds divided by 28 centimeters minus 2 centimeters. And that is supposed to be equal to 4 pi squared divided by the experimental value for g. Therefore, the experimental value that we are looking for has to be equal to 4 pi squared divided by that slope, which as a decimal value is approximately 0.0462 squared seconds over centimeters. Now, under these circumstances, the experimental value for g that we are obtaining is 855, and the reason for this value in the hundreds is that it's given as centimeters per second squared. So if you want it as a more standard value, that's 8.55 meters per second squared, which you get by simply dividing by 100 centimeters in 1 meter. And that is the answer that they were requesting in part B, an experimental value for the gravitational acceleration. Now, it is clear that this acceleration is not very standard or accurate for Earth. I mean, 9.8, 9.81, 8.55, what's going on here? So let's look at it from the point of assessing how accurate the value is. When they give you an experiment like this, it's clear that you can calculate how close or far away from the accepted value the value that you want is. They tell you that the apparatus allows an accuracy of 4%. Means that if you are within 4% of the accepted value, you should be okay. But the accepted value is 9.80 meters per second squared. So what they are asking is, this experimental value, 8.55 meters per second squared, is it within reasonable agreement of the accepted value of 9.80 meters per second squared? Well, if you want to determine agreement within 4%, you need to calculate the percent error. And that percent error is given by the formula absolute value of the accepted value minus the experimental value. Basically, that's the difference between accepted and experimental values, divided by the accepted value, and you multiply times 100 to give the error as a percentage. So you are going to calculate the absolute value of 9.80 meters per second squared minus 8.55 meters per second squared. Divide that by 9.80 and multiply times 100, and what you get is a 12.8% error. So what you are forced to say is that no, there is no agreement. Okay, there is no agreement of the experimental value gexp with the accepted value 9.80 meters per second squared. So what's the reason for this disagreement? Well, they give you some more information now. They tell you that someone gives you the information that this experimental apparatus is, in fact, on Earth or close to Earth's surface, but that the experiment has been conducted inside an elevator that is moving with a constant acceleration. Assuming that your experimental value is exact, which means basically you can say that the calculation that gexp is 8.55 is correct, then you want to determine the magnitude and the direction of the elevator's acceleration. So what are we talking about here? Basically, the idea is if the elevator is accelerating, that affects the period of the pendulum because the net gravity is not what you would expect. The pendulum is supposed to be moving back and forth, but you're supposed to have a vertical acceleration. We're not sure now whether it's up or down, but what we are saying is, consider that for the pendulum, the acceleration is 8.55 meters per second squared. We can call this an apparent acceleration. And this apparent acceleration is due to the fact that the elevator is itself accelerating. Now, if you consider, for example, some other objects here, like imagine there's a table, and on that table there is a book. What would be the forces acting on that book? Well, obviously, what you will have as forces are the gravitational force, m times g, and the normal force, which gives you the apparent weight. That normal force, because it's the apparent weight, or the weight that you're supposed to measure with a scale, is going to be the mass times the experimental or measured acceleration. These two forces are not equal because the book is also accelerating the same as the pendulum. So you could say basically that any object inside of this elevator is having, of course, a force due to gravity, which is m times g accepted, the usual 9.80, and then it's going to have a normal force that is slightly less. It's the mass times g experimental. And so what we can establish is that the normal force here, the normal force is given by the difference between these two. And that normal force is going to be the mass of the object times the acceleration that you're looking for. Now, this means that if we take positive downward to make a simpler calculations, mass times the g accepted minus the mass times G experimental is equal to the mass times the acceleration of the whole elevator. Now the mass cancels, and so what we have is G accepted minus G experimental is equal to the acceleration you're looking for. So you have 9.80 meters per second squared down, 8.55 meters per second squared up, and that's your acceleration. Therefore, the acceleration you are looking for is 1.25 meters per second squared, and its direction is down because the higher force is going down. So this elevator is accelerating down at 1.25 meters per second squared, and that's the answer that you wanted. Basically, you can clear up this idea by thinking, what's going to happen if the elevator starts in free fall? If somehow the cable for the elevator breaks down and the elevator starts accelerating at 9.80 downward, then the pendulum is not going to be able to swing. It's just going to stay in a position and not swing at all because nothing is pulling it. So that's a nice analysis of what happens with the pendulum under acceleration. I invite you to consider it further and thank you for your attention. Have a nice one. See you next problem.